Good evening and welcome to Dreams of Gravity. Thank you for being here tonight, for choosing this moment to step away from the rush of the day and settle into something quieter, something slower. Before we begin, I'd like to invite you to get comfortable, to lie down if you can, to dim the lights, to let your shoulders drop and your breathing soften. There's nowhere you need to be right now, nothing you need to do. Just listen and let yourself drift gently into the story of the universe, into the deep and beautiful mystery of what everything is made of and where it all comes from. Tonight, we're going to explore an idea, a question really, one that sits at the edge of science and philosophy, a question that feels almost like poetry. What if matter, all the solid, heavy, tangible stuff that makes up our world, our bodies, the ground beneath us, the stars above us, what if all of it is actually light? Just light that has somehow slowed down and taken on a stable form? What if the difference between a beam of sunlight and a grain of sand is simply a matter of speed, of stillness, of light that has decided to pause and become something else for a while? It's a strange thought, isn't it? And yet, when you look out into the cosmos, when you let your mind wander through the vast distances between galaxies, through the swirling arms of nebulae, through the quiet orbits of distant planets, you begin to see that the universe is not made of separate things at all. It's all one continuous dance, one endless transformation, light becoming matter, matter releasing light, energy folding into form and then unfolding again, over and over, like the tide of an infinite ocean. Let's begin there, with the galaxies. Imagine them, if you will, not as static islands of stars, but as living, breathing systems, each one a slow waltz of billions of suns, each one spinning gracefully through the darkness. Galaxies move like water, like clouds, like the slow drift of continents across the surface of a planet. They collide, they merge, they spiral around one another for millions of years before finally becoming one. And all of this happens in silence, in the deep and patient silence of space, where time itself moves differently, where a million years is just a heartbeat and a single human life is barely a flicker. From a distance, galaxies look like glowing pools of light, scattered across the darkness like lanterns floating on a calm sea. And in a way, that's exactly what they are. They are light, concentrated, and gathered into forms that we can see. Light that has been woven into stars and planets and dust. Light that has slowed down just enough to become something we might call solid, something we might call real. But the truth is, nothing in the universe is truly solid. Everything is mostly empty space, mostly energy, mostly light in one form or another, moving at different speeds, vibrating at different frequencies, playing different notes in the great symphony of existence. Think about the structure of a galaxy for a moment. Most galaxies are spiral in shape, with long, graceful arms that sweep outward from a bright central bulge, like a cosmic pinwheel frozen in the act of spinning. These spiral arms are not solid structures, not fixed features that rotate as a single piece. Instead, they're density waves, regions where stars and gas and dust gather more densely for a time, creating the appearance of arms, and then disperse again as they orbit the galactic center. It's like a traffic jam on a highway that never really moves, where cars flow into it and out of it, but the jam itself stays in roughly the same place. The stars pass through the spiral arms the way you might pass through a cloud, briefly part of something larger, and then moving on, continuing their own individual orbits around the galaxy's heart. And there's something meditative about this rhythm, about the way galaxies breathe, the way they inhale matter and exhale light, the way they grow and evolve over billions of years. If you could speed up time, if you could watch a galaxy the way you might watch a flower bloom, you'd see it pulsing, expanding, contracting, its arms winding tighter and then loosening, stars being born in bright bursts of blue and white, then aging and reddening, then dying and scattering their remains back into the interstellar medium, feeding the next generation. It's a cycle, a wheel, a great cosmic metabolism that never stops, that never tires, that simply is, the way a river is, the way the ocean is, the way your own breath is as you lie there listening. The spiral arms themselves are sites of tremendous activity, places where the density of gas and dust becomes high enough to trigger new episodes of star formation. When gas clouds encounter these density waves, they're compressed, squeezed together by the gravitational pressure of all the surrounding matter, and this compression can push them past a critical threshold, causing them to collapse and fragment into smaller pieces, each piece potentially becoming a new star. It's a cascading process, one that feeds on itself, because once new stars form, their light and their stellar winds can trigger even more compression in neighboring clouds, creating waves of star formation that ripple through the galaxy like the spreading rings when you drop a stone into still water. And at the center of most galaxies, including our own Milky Way, there lies a supermassive black hole, a gravitational anchor that holds the entire system together, a dark and silent presence millions or billions of times more massive than the Sun. These black holes don't actively consume everything around them. They're not cosmic vacuum cleaners destroying all they encounter. Instead, they sit quietly at the center, their gravity shaping the orbits of billions of stars, their presence felt across thousands of light years of space. A reminder that even in the vastness of the cosmos, there are places where matter becomes so dense, so concentrated, that not even light can escape. But even these black holes are not eternal destroyers. They're more like the heart of the galaxy, pumping energy outward through jets and winds, regulating the rate at which new stars can form, maintaining a delicate balance between creation and destruction. When matter falls toward a black hole, it doesn't simply disappear. It heats up, it glows, it emits tremendous amounts of radiation, sometimes outshining all the stars in the galaxy combined. And this radiation pushes back on the surrounding gas, preventing it from falling in too quickly, creating a kind of feedback loop that determines how the galaxy evolves, how big it grows, what shape it takes. It's a self-regulating system, a kind of cosmic thermostat that keeps the galaxy from burning through all its fuel too quickly, ensuring that star formation can continue for billions of years. Now, let's drift closer. Let's imagine we're moving through one of these galaxies, gliding past its outer stars, its spiral arms, its glowing core. And we find ourselves approaching a solar system, a star with a family of planets circling around it, each one tracing its own invisible path through space. Planets move like dancers, each one following its own rhythm, its own orbit, its own relationship with the star at the center. Some move quickly, whipping around in a matter of days. Others take decades, centuries even, to complete a single circuit. And yet, each one is perfectly balanced, held in place by gravity, by the gentle pull of the star's light and warmth, by the invisible forces that keep the whole system from flying apart. Consider for a moment the delicate balance that makes a planetary system possible. If a planet is too close to its star, the heat becomes unbearable, the surface melts, any atmosphere is stripped away by the stellar wind. If it's too far, everything freezes. Water becomes ice, the air itself condenses and falls as snow. But in between, there's a narrow band, a zone where conditions are just right, where water can exist as a liquid, where the temperature allows for complexity, for chemistry, for the possibility of life. We call this the habitable zone. Though in truth, life might find ways to exist in places we'd never expect. In the frozen oceans beneath the ice shells of distant moons, in the clouds of Venus, in the underground caves of Mars where liquid water might still flow. And think about the planets themselves, each one a world, each one with its own character, its own personality in a sense. Jupiter, massive and stormy, with its great red spot, a hurricane that has raged for centuries, large enough to swallow the Earth whole. Saturn, ringed and serene, its rings made of countless chunks of ice and rock, each one orbiting independently, creating a structure so thin you could pass through it in a spaceship without much difficulty, and yet so vast it stretches for hundreds of thousands of kilometers. Neptune and Uranus, distant ice giants, blue and green, tilted on their sides, orbiting in the cold outer reaches of the solar system where the sun is just another bright star in the sky. Each of these planets tells a story about how solar systems form, about the conditions in the early disk of gas and dust that surrounded the young sun. The rocky inner planets, Mercury, Venus, Earth and Mars, formed close to the star where it was too hot for ice and other volatile materials to condense, so they're made primarily of rock and metal, the heavy stuff that can withstand high temperatures. The giant planets formed farther out, beyond what we call the frost line, where it was cold enough for water and other ices to freeze, allowing them to grow much larger by accumulating vast atmospheres of hydrogen and helium, the lightest and most abundant elements in the universe. And what is gravity, really, but another form of relationship between matter and light? Einstein showed us that gravity is not a force pulling objects together, but a bending of space and time itself, a curvature caused by the presence of mass and energy. Imagine space as a vast, soft fabric, stretched out in all directions, and imagine placing a heavy ball in the center of it. The fabric bends, curves inward, and anything nearby will naturally roll toward the ball, not because it's being pulled, but because the shape of the fabric itself has changed. That's gravity. That's how planets orbit stars, how moons orbit planets, how galaxies hold themselves together. It's all a matter of geometry, of the way energy shapes the space around it, of light bending the universe into form. But there's something even more profound here. Einstein's equations tell us that not just mass, but any form of energy curves space and time. Light itself, pure electromagnetic radiation with no mass at all, still bends space, still creates gravity, still participates in the cosmic dance. A beam of light passing near the sun is deflected slightly, its path curved by the sun's gravity. And in turn, that light, by carrying energy, contributes its own tiny amount to the curvature of space. It's a relationship, a conversation between energy and geometry, between what exists and the shape of existence itself. And there's a beautiful symmetry to this. Light affects space, and space affects light. Matter curves space, and curved space tells matter how to move. Everything is interconnected. Everything influences everything else, and nothing exists in isolation. When you move your hand, you're creating ripples in space-time, infinitesimally small ripples, far too small to measure with any instrument we have, but real nonetheless. When two black holes collide billions of light years away, they send waves through space-time, gravitational waves that travel across the universe at the speed of light. And when they reach Earth, they cause space itself to stretch and compress by less than the width of an atomic nucleus. And yet, we can detect them. We've built instruments sensitive enough to feel the universe trembling, to hear the echoes of collisions that happened before the Earth existed. These gravitational wave detectors, massive facilities like LIGO and Virgo, use laser beams that travel back and forth along tunnels several kilometers long, bouncing between mirrors, creating interference patterns that are extraordinarily sensitive to any change in the distance between those mirrors. When a gravitational wave passes through, it stretches space in one direction and compresses it in the perpendicular direction, changing the lengths of the detector arms by an amount so small that it defies imagination. And yet we can measure it. We can hear the universe singing, the deep bass notes of colliding black holes, the higher-pitched chirps of merging neutron stars, a cosmic symphony that has been playing for billions of years, but which we've only recently learned to listen to. And the planets themselves, what are they made of? Rock, metal, gas, ice, all different kinds of matter, all different expressions of the same fundamental ingredients. And if we look closely, if we zoom in far enough, we find that every atom, every molecule, every particle is mostly empty space. The solid ground beneath your feet, the walls around you, the air you breathe, it's all made of atoms, and atoms are almost entirely nothing. At the center of each atom is a tiny nucleus made of protons and neutrons, and around it, far, far away on the atomic scale, are the electrons, tiny points of charge that orbit the nucleus like distant planets. And between them, there is nothing, just empty space, just the hum of electromagnetic fields holding it all together. To get a sense of the scale, imagine the nucleus of an atom expanded to the size of a marble. On that scale, the nearest electron would be orbiting somewhere about 0.5 kilometer away. Everything in between, all that space, is empty, or at least as empty as anything in the quantum realm can be. It's filled with fields, with potential, with the possibility of interactions. But there's no stuff there, no material, no solid thing you could point to and say, this is what matter is made of. And yet, when trillions upon trillions of these mostly empty atoms come together, they create the illusion of solidity, the sensation of resistance when you push against a wall, the feeling of weight when you hold something in your hand. What we experience as solidity is really just electromagnetic repulsion, electrons pushing against electrons, fields interacting with fields, creating the sensation of contact, of resistance, of substance. When you sit in a chair, you're not really touching it in the classical sense. Your atoms and the chair's atoms are hovering incredibly close to one another, but never actually making contact, held apart by the electromagnetic forces that govern how matter behaves. It's like two magnets with the same poles facing each other, pushing apart, creating a barrier that feels solid, but is really just force, just field, just energy arranged in a particular pattern. And when you touch something, when you feel its texture, its temperature, its hardness or softness, what you're really sensing is the way those electromagnetic fields interact with the fields of your own atoms. The way energy transfers from one configuration to another. Temperature is molecular motion, the average kinetic energy of atoms jiggling and vibrating. Hardness is the resistance of those electromagnetic fields to deformation. Texture is the pattern of microscopic variations in how those fields are arranged. Everything you perceive as physical, as material, as real, is actually just patterns of energy, waves and fields interacting in complex and beautiful ways. But here's the beautiful part. Those protons, those neutrons, those electrons, they're not little balls of solid stuff. They're not hard and permanent and unchanging. They're waves, patterns of energy, disturbances in invisible fields that fill all of space. They're vibrations, frequencies, notes in a song that has been playing since the beginning of time. And those vibrations, that energy, it all comes from light. It all comes from the same source, the same fundamental force that shines from the sun, that travels across the emptiness of space, that warms your skin on a summer day. In the language of quantum field theory, every particle is an excitation of its corresponding field. The electron is a ripple in the electron field. The quark is a ripple in the quark field, and so on. But all these fields are interconnected, all part of a deeper structure that physicists are still trying to fully understand. Some theories suggest that at the most fundamental level, there might be just one field, one unified entity from which all particles and forces emerge, like different notes played on the same cosmic instrument. And if that's true, then the distinction between matter and light, between particles with mass and particles without mass, becomes even more blurred, even more a matter of perspective than a fundamental difference. String theory, one of the most ambitious attempts to unify all the forces and particles of nature, suggests that at the smallest possible scale, far smaller than atoms, smaller than protons, smaller than anything we can currently observe, everything is made of tiny vibrating strings of energy. Different patterns of vibration correspond to different particles. An electron is a string vibrating one way. A quark is a string vibrating another way. A photon is yet another pattern. It's all music, all harmony, all rhythm playing out at scales so small that we may never be able to observe them directly. And yet those tiny vibrations determine everything about the universe we experience. And there's something profound about thinking of reality as music, as vibration, as patterns of energy resonating in harmony and discord. It's not just a metaphor, it's a deep mathematical truth embedded in the equations that describe how the universe works. The Schrödinger equation, which governs the behavior of quantum systems, is a wave equation, describing how patterns of probability amplitude propagate through space and time. The solutions to this equation are standing waves, patterns that repeat, that resonate, like the harmonics of a plucked string or the overtones of a struck bell. The stable states of atoms, the orbitals where electrons can exist, they're determined by which standing wave patterns can fit around the nucleus, which harmonics resonate, which notes can be played. By the way, I wonder, where are you watching from tonight? Which city and what time of day is it for you right now? Perhaps it's late. Perhaps the stars are already out above you. Or perhaps you're somewhere where the sun is just beginning to set, painting the sky in shades of orange and gold. Wherever you are, whatever time it is, you're part of this same universe, made of the same light, the same energy, the same ancient stardust that has been cycling through the cosmos for billions of years. Now, let's talk about the stars themselves, because stars are where this story really begins to make sense. Stars are born in clouds of gas and dust, vast nebulae that stretch across light years of space, dark and cold and silent. These molecular clouds, as astronomers call them, are the coldest places in the galaxy, with temperatures hovering just a few degrees above absolute zero. They're made primarily of hydrogen, the simplest and most abundant element, along with helium and traces of heavier elements, all mixed together with tiny grains of dust, particles of carbon and silicon and ice that formed in the atmospheres of dying stars and were blown out into space. And then, slowly, over millions of years, gravity begins to pull the cloud inward, drawing the gas and dust together, compressing it, heating it. The process starts with small perturbations, tiny fluctuations in density that might be caused by a passing star, by the shock wave from a distant supernova, by the collision of two clouds, or even by the random quantum fluctuations that are always present in any system. These perturbations grow, amplified by gravity, and as they grow, they begin to fragment the cloud into smaller and smaller pieces, each piece collapsing under its own weight, each one potentially becoming a star. This is the process astronomers call fragmentation, and it's what allows a single cloud to give birth not to one star, but to dozens, hundreds, even thousands of stars, all forming roughly at the same time in what we call a stellar nursery or a star-forming region. The Orion Nebula, visible to the naked eye as a fuzzy patch in the Sword of Orion, is one of these nurseries, a place where new stars are being born right now, where you can see in real time, or at least on astronomical timescales, the transformation of gas into stars, of potential into kinetic, of chaos into order. As each fragment of the cloud continues to collapse, it gets denser and hotter. The gravitational potential energy of the infalling gas is converted into thermal energy, into heat, raising the temperature at the core. At first, this heat can radiate away, carried off by photons escaping from the cloud. But as the density increases, the cloud becomes opaque, trapping the heat inside, and the temperature begins to rise more rapidly. The collapsing fragment becomes what astronomers call a protostar, a star in the making, not yet hot enough to sustain nuclear fusion, but already glowing from the heat of its gravitational contraction. The protostar continues to grow, accreting matter from the surrounding cloud, pulling in gas and dust that spiral down onto its surface through an accretion disk, a flattened structure of orbiting material that looks like a miniature version of a galaxy or the rings of Saturn. This disk is where planets will eventually form, where the leftover material from star formation will coalesce into rocky worlds and gas giants and all the other bodies that make up a solar system. But for now, it's just feeding the star, adding mass, adding energy, pushing the temperature and pressure at the core ever higher. And then, finally, at the very center, when the temperature reaches about 10 million degrees Kelvin, something miraculous happens. The atoms begin to fuse together. Hydrogen, the simplest and lightest element, begins to merge, two nuclei overcoming their electromagnetic repulsion through sheer thermal energy, colliding with enough force to stick together, fusing into helium, and releasing a tremendous burst of energy in the process. And that energy is light, pure radiant light, streaming outward in all directions, pushing back against the crushing weight of gravity, holding the star in perfect balance. And so, a star is born, a sphere of glowing plasma, a furnace where matter is constantly being transformed into light, where mass is being converted into energy, according to the most famous equation in all of physics, Einstein's E equals mc squared. That equation tells us that energy and mass are two sides of the same coin, that they can be transformed into one another, that a tiny amount of mass contains an almost unimaginable amount of energy. In the heart of a star, every second, millions of tons of hydrogen are converted into helium, and in the process, a tiny fraction of that mass, less than 1%, is turned into pure energy, into photons, into light. The process of fusion is delicate and precise. It requires temperatures of millions of degrees, pressures so intense that atoms are stripped of their electrons and exist as bare nuclei, moving so fast that they can overcome the electric repulsion that normally keeps them apart. The actual mechanism by which hydrogen fuses into helium involves several steps, a chain of reactions that astronomers call the proton-proton chain, or, in more massive stars, the CNO cycle, where carbon, nitrogen, and oxygen act as catalysts, facilitating the fusion without being consumed themselves. When two hydrogen nuclei, two protons, collide with enough force, they can stick together through the weak nuclear force, one of the protons transforming into a neutron and emitting a positron and a neutrino in the process. This creates deuterium, heavy hydrogen, which can then capture another proton to form helium-3, which in turn can combine with another helium-3 to form helium-4, releasing two protons back into the mix. It's an intricate dance, a carefully choreographed sequence of steps that converts 4 hydrogen nuclei into one helium nucleus, releasing energy in the form of gamma rays, high-energy photons that begin a long journey from the core of the star to its surface. That journey can take thousands, even hundreds of thousands of years, as the photons bounce and scatter and are absorbed and re-emitted countless times, gradually losing energy, shifting from gamma rays to X-rays, to ultraviolet to visible light, until finally they reach the surface and stream out into space as the light we see. Think about that for a moment. The sunlight that warms your face on a spring morning, that light was created in the core of the sun hundreds of thousands of years ago, long before human civilization existed, long before our ancestors walked upright, long before mammals dominated the earth. That photon has been on a journey, bouncing around inside the sun, gradually working its way outward, and only now, only in this moment, does it finally escape and travel the 8 light minutes to Earth to touch your skin. It's ancient light, carrying within it the energy of fusion reactions that happened in another era. And yet it arrives fresh and new, as vibrant and alive as the moment it was born. And stars come in many varieties, many sizes and colors and temperatures. Small red dwarfs, barely massive enough to sustain fusion, burning so slowly and efficiently that they might shine for trillions of years, longer than the current age of the universe. These tiny stars, with masses less than half that of the Sun, are by far the most common type of star in the galaxy, outnumbering all other types combined, and yet they're so faint that not a single one is visible to the naked eye from Earth. They glow with a dull red light, Their surfaces cool enough that you could, in principle, hold your hand close to one without being instantly vaporized, though the radiation and the lack of atmosphere would kill you in other ways. Medium-sized stars like our Sun, yellow and stable, with lifespans of billions of years, long enough for planets to form around them, for life to emerge, for civilizations to rise and fall. The Sun has been shining for about 4.6 billion years, and it will continue to shine, relatively unchanged, for another 5 billion years or so, giving Earth and whatever life exists on it ample time to evolve, to adapt, to perhaps even leave the planet and spread to other worlds before the Sun finally runs out of hydrogen in its core and begins the next phase of its evolution. And massive blue giants, burning bright and hot and fast, exhausting their fuel in just a few million years, living fast and dying young in spectacular explosions. These stars, with masses 10, 20, 50 times that of the Sun or even more, shine with a fierce blue-white light, their surfaces scorching hot, their cores burning through hydrogen, helium, carbon, oxygen, silicon, one element after another, in a frantic race against gravity. They live brief, brilliant lives, and when they die, they do so catastrophically in supernova explosions that can briefly outshine an entire galaxy. And when a massive star reaches the end of its life, when it has burned through all its fuel and has nothing left to hold it up against gravity, it collapses inward in a fraction of a second and then explodes outward in a supernova, a burst of light so bright that it can outshine an entire galaxy. In that explosion, all the heavy elements are scattered into space. Iron and gold and carbon and oxygen, all the ingredients needed to make planets, to make life, to make you and me. We are, quite literally, made of stardust, made of the remnants of ancient suns that lived and died billions of years ago, made of light that has been slowed and shaped and transformed into something stable, something that can last, something that can think and feel and wonder about its own origins. There's a profound poetry to this. Every carbon atom in your body, every oxygen atom, every atom of iron in your blood was forged in the nuclear furnace at the heart of a star or in the violent explosion of a supernova. The calcium in your bones, the phosphorus in your DNA, the sulfur in your proteins, all of it came from stars. You are not just in the universe, you are of it, woven from its fabric, assembled from its ingredients, animated by its energy. When Carl Sagan said, "We are star stuff," he wasn't speaking metaphorically. It's the literal truth, the most fundamental fact about what we are and where we come from. And there's something deeply moving about tracing your lineage back, not just through your parents and grandparents and distant ancestors, but back through the whole history of life on Earth, back through the formation of the planet, back through the birth of the solar system, back through the death of earlier stars, back through the formation of the first galaxies, back to the Big Bang itself. You are 14 billion years old. Every atom in your body is 14 billion years old. You carry within you the memory of the beginning, encoded not in your mind, but in the very substance of your being, in the quarks and electrons that make up your atoms, in the patterns of energy that give you form. The elements that make up your body, that make up the Earth, that make up everything you've ever touched or seen, they have stories, histories that stretch across billions of years and trillions of kilometers. That iron in your blood, it was forged in the core of a massive star that exploded long before the solar system existed, its atoms scattered into space, incorporated into a new cloud of gas that eventually collapsed to form the sun and the planets. That calcium in your bones, it came from a different star perhaps, or from the same one, mixed together in the cosmic recycling bin of the interstellar medium, waiting patiently for billions of years until the right conditions came along for it to be incorporated into a rocky planet, then into living organisms, and finally into you. And so we come back to our question. What if matter is light slowed into a stable form? It sounds like a metaphor, like a poetic way of describing the universe, but there's a deep truth to it, a truth that lies at the heart of modern physics. Light, as we experience it, is a wave of energy that travels through space at the fastest possible speed, about 300,000 kilometers per second. It has no mass, no weight, no resistance to motion. It simply moves endlessly until it encounters something that absorbs it or reflects it. But light is also made of particles, tiny packets of energy called photons, and photons are strange things. They have no mass, and yet they carry energy and momentum. They can push against things, they can exert force, they can bend and curve around massive objects. And here's where it gets truly interesting. According to the equations of quantum field theory, the deepest and most accurate description of reality that we have, every type of particle, every form of matter is actually a vibration in an underlying field, a kind of invisible fabric that fills all of space. There's a field for electrons, a field for quarks, a field for photons. And when these fields vibrate in just the right way, particles appear. An electron is a ripple in the electron field. A quark is a ripple in the quark field. And a photon is a ripple in the electromagnetic field. But all these fields are connected. All these particles are related because they all emerge from the same underlying structure, the same fundamental framework of space and time and energy. And in the very early universe, in the first moments after the Big Bang, when everything was unimaginably hot and dense, all the particles we know today didn't exist yet. There was only energy, only light, only a seething ocean of radiation so intense that matter as we know it couldn't form. Particles and antiparticles were constantly being created and destroyed, flashing into existence for a fraction of a second before annihilating each other and turning back into pure energy. The early universe was a furnace, a cauldron of pure light and energy, with temperatures so high that individual particles couldn't maintain their identity, couldn't condense into stable forms. Imagine a pot of water boiling so vigorously that you can't distinguish individual drops, can't see where one molecule ends and another begins, just a churning mass of steam and liquid and energy. That's what the early universe was like, except instead of water molecules, it was quarks and gluons and photons and all manner of exotic particles, all mixed together in a state of matter so extreme we can only recreate it for brief moments in our most powerful particle accelerators. In those first microseconds after the Big Bang, the universe was dominated by radiation, by light, by photons careening through space at the speed of light, colliding with particles, creating new particle-antiparticle pairs, which would then annihilate back into photons. It was a state called thermal equilibrium, where energy constantly shifted forms but maintained an overall balance, where creation and destruction happened at equal rates, where nothing could settle, nothing could last. But then, As the universe expanded and cooled, something changed. The energy density dropped, the temperature fell, and suddenly it became possible for particles to stick around, to survive, to become stable. Quarks began to combine into protons and neutrons, a process called hadronization that happened when the universe was about 1 microsecond old and had cooled to a mere trillion degrees or so. Protons and neutrons began to form the nuclei of atoms through a process called Big Bang nucleosynthesis, which lasted for about the first 20 minutes of cosmic history and produced mostly hydrogen and helium, with traces of lithium and beryllium, but nothing heavier. And eventually, after hundreds of thousands of years, the universe cooled enough for electrons to settle into orbit around those nuclei, forming the first atoms, mostly hydrogen and helium, the simplest elements, the building blocks of everything that came after. This moment, when electrons and nuclei combine to form neutral atoms, is called recombination, and it marks one of the most important transitions in cosmic history. Before recombination, the universe was opaque, a thick fog of charged particles that scattered light in every direction, making it impossible for photons to travel very far. But once neutral atoms formed, the universe became transparent, and light could suddenly travel freely through space. The photons that were released at that moment, about 380,000 years after the Big Bang, are still traveling through the universe today. We call this the cosmic microwave background radiation, and it's one of the most important pieces of evidence we have for the Big Bang theory. These photons have been stretched and redshifted by the expansion of the universe, cooled from thousands of degrees to just a few degrees above absolute zero. But they're still here, filling all of space with a faint glow that we can detect with sensitive instruments. When you tune a radio or television to a channel with no station, a small fraction of the static you see and hear is actually this ancient light, the oldest light in the universe, the echo of the Big Bang itself. And so, in a very real sense, matter is just light that has slowed down, energy that has taken on a stable form, vibrations in invisible fields that have somehow become persistent, lasting, tangible. The chair you're sitting in, the screen you're looking at, the body you inhabit, it's all made of atoms. And atoms are made of particles, and particles are made of energy. And energy, at its most fundamental level, is light, is motion, is the endless dance of the universe unfolding itself moment by moment. Scientists have actually found ways to slow light down in the laboratory, not just metaphorically, but literally. By passing light through specially prepared materials, through clouds of ultra-cold atoms cooled to within a fraction of a degree above absolute zero, they've managed to reduce its speed from 300,000 kilometers per second to less than 100 kilometers per hour, slower than a car on a highway. They've even managed to stop light completely, to freeze it in place, to trap it within a medium, and then release it again, all without losing the information it carries. It's a remarkable achievement, and it gives us a glimpse of the deep connection between light and matter, the way they can transform into one another, the way they're really just different aspects of the same underlying reality. When light enters a material, it doesn't just pass through unchanged. It interacts with the atoms, with the electrons orbiting the nuclei, setting them into motion, creating tiny oscillations, tiny vibrations that then emit their own light. This newly emitted light interferes with the original beam, and the combination of the two creates a wave that appears to move more slowly than light in a vacuum. The photons themselves are still moving at the speed of light, but the effective speed of the wave, the speed at which information and energy propagate, can be dramatically reduced. It's as if the light is taking a longer, more complicated path through the material, bouncing from atom to atom, being absorbed and re-emitted over and over, each interaction adding a tiny delay, and all those delays adding up to a significant slowing of the overall wave. And in some exotic materials, in carefully engineered structures, light can be slowed so much that it almost seems to stop, to hover, to become trapped in a particular location. Researchers have created what they call stopped light systems, where photons are absorbed by a cloud of atoms and stored as quantum states, as patterns of excitation that preserve all the information the light carried, and then later, when conditions are right, those patterns can be converted back into photons and released, the light continuing its journey as if nothing had happened. It's a kind of matter-light transformation, a demonstration that the boundary between the two is not as sharp as we might think, that under the right circumstances, light can become matter-like, trapped and localized, and matter can become light-like, radiating energy and information. Now, let's think about time for a moment, because time and light are intimately connected. Light moves at the speed of light, obviously, and according to Einstein's theory of relativity, the speed of light is the same for everyone, no matter how fast they're moving or where they are in the universe. It's a universal constant, a kind of cosmic speed limit that nothing can exceed. And because the speed of light is constant, time itself must be flexible. Time can stretch and compress, speed up and slow down, depending on how fast you're moving and how strong the gravity is around you. Imagine you're traveling on a spaceship, moving at a significant fraction of the speed of light. From your perspective, everything inside the ship feels normal. Time ticks along at its usual pace. Your heart beats, your thoughts flow, everything is ordinary. But to someone watching you from Earth, you appear to be moving in slow motion. Your clocks run slower, your aging slows down, your entire existence is stretched out in time. And if you were somehow able to travel at the speed of light, which is impossible for anything with mass, time would stop entirely. For a photon, for a particle of light, there is no time. The moment it's emitted from a star, and the moment it's absorbed by your eye, those are the same instant from the photon's perspective. It doesn't experience time at all. It exists in a kind of eternal now, a timeless present where beginning and end are the same thing. And so, when light slows down, when it becomes matter, time begins to matter. Time becomes relevant, becomes something that can be measured and experienced. Matter exists in time, it changes, it evolves, it grows and decays and transforms. Light, pure light, exists outside of time. But matter, stable matter, is light that has entered into time. Light that has agreed to participate in the slow unfolding of the universe. The patient process of stars being born and dying, of galaxies swirling through space, of planets forming and life emerging, and consciousness awakening to contemplate its own existence. There's something deeply moving about this relationship between light and time. We measure our lives in time, in years and days and hours and moments. We experience time as a flow, a current that carries us from birth to death, from past to future, from memory to anticipation. And yet, at the most fundamental level, time is not a river that flows, but a dimension, a coordinate, a way of organizing events in relation to one another. And the ultimate arbiter of time, The thing that defines its structure and its properties is light. The speed of light is not just the speed at which photons move, it's the speed at which causality propagates, the speed at which information can travel from one place to another, the speed at which the universe itself unfolds. And time, like space, is not absolute. It's relative, dependent on the observer, on their motion and their position in gravitational fields. Near a black hole, time slows to a crawl. In empty space, far from any massive objects, time flows at its maximum rate. On Earth, at sea level, time runs slightly slower than it does on a mountain top, because the gravitational field is slightly stronger at lower altitudes. The difference is tiny, measured in billionths of a second per day, but it's real, and it's measurable, and it has practical consequences. The GPS satellites that guide our navigation systems have to account for relativistic time dilation, both from their motion in orbit and from the weaker gravitational field they experience. If we didn't correct for these effects, GPS would quickly become inaccurate, errors accumulating by meters per day, making the system useless. Let's drift now toward the most mysterious objects in the universe, the black holes, places where matter and light and time all become tangled together in ways that stretch our understanding to its limits. A black hole is what happens when a massive star dies and collapses in on itself, when gravity becomes so intense that nothing, not even light, can escape. At the center of a black hole is a singularity, a point where all the mass is compressed into an infinitely small space, where the laws of physics, as we know them, break down completely. And surrounding the singularity is the event horizon, the boundary of no return, the invisible line that separates the inside of the black hole from the rest of the universe. If you were to approach a black hole, you would find that time behaves in very strange ways. As you get closer and closer to the event horizon, time slows down from the perspective of someone watching from far away. They would see you moving slower and slower, your image becoming redder and fainter as the light from your body is stretched and delayed by the intense gravitational field, until finally, at the horizon itself, you would appear to freeze, to become a motionless image, suspended forever at the edge of the abyss, gradually fading into invisibility as the photons carrying your image become infinitely redshifted. But from your own perspective, nothing strange happens. You cross the horizon smoothly, you continue falling inward, and you never notice anything unusual about the passage of time. It's only when you try to communicate with the outside universe that you realize something is wrong, that your signals are being stretched and delayed, that the universe you left behind is speeding up, aging faster and faster until billions of years pass in what feels like moments. If you could somehow look back toward the universe as you fell through the event horizon, you would see the entire future history of the cosmos unfold before your eyes, galaxies forming and dissolving, stars living and dying, the universe expanding and perhaps eventually ending, all compressed into the brief moment of your fall. And what happens to light near a black hole? Light, which normally travels in straight lines, is bent and curved by the intense gravity, following the warped geometry of space and time. Some light spirals inward, crossing the event horizon and disappearing forever, adding its energy to the black hole's mass. Other light orbits the black hole, trapped in circular paths at a distance called the photon sphere, racing around and around, never quite falling in, never quite escaping, caught in a precarious balance between gravity and momentum. And some light, if it's moving in just the right direction, can slingshot around the black hole and be flung back out into space, carrying with it the imprint of that encounter, the memory of having brushed against the edge of oblivion. Its wavelength shifted, its path bent, its information encoded with the signature of the black hole's gravity. Black holes are not just objects in space. They're features of space-time itself, places where the fabric of reality becomes so severely curved that it folds in on itself, creating a pocket of causally disconnected space from which nothing can return. And yet, even black holes are not eternal. Stephen Hawking showed that black holes emit radiation, a slow trickle of particles and photons that gradually carry away their mass and energy. Over unimaginably long timescales, longer than the current age of the universe by many orders of magnitude, even the largest black holes will evaporate, will dissolve back into the quantum foam, returning their stolen light to the cosmos. The mechanism of Hawking radiation is subtle and beautiful. At the quantum level, space is not empty, but filled with virtual particles, pairs of particles and antiparticles that spontaneously appear and then immediately annihilate each other, flashing into existence for such a brief moment that they don't violate the conservation of energy, borrowing energy from the quantum uncertainty principle and paying it back before anyone can notice. But near the event horizon of a black hole, something strange can happen. If a virtual pair appears right at the edge, one particle might fall into the black hole while the other escapes. To an outside observer, it looks like the black hole is emitting a particle, giving off radiation. And because energy must be conserved, the black hole must lose a tiny bit of mass for each particle that escapes. The energy coming from the black hole's gravitational field, from the very fabric of curved space-time itself. Over time, this process causes the black hole to shrink, to evaporate, to slowly give back everything it has consumed. And as a black hole shrinks, its temperature increases, and it radiates faster and faster in a runaway process that ends in a final burst of energy when the last of the mass is converted back into radiation. It's a beautiful symmetry, a reminder that nothing in the universe is permanent, that even the most extreme objects, the densest concentrations of matter, the deepest wells of gravity, eventually dissolve back into light, back into energy, back into the quantum fields from which everything emerges. And beyond the black holes, out in the vast spaces between the stars, there are the nebulae, the birthplaces and the graveyards of stars, glowing clouds of gas and dust that stretch across light years of space. Some nebulae are bright and colourful, lit from within by young, hot stars that have just been born, their ultraviolet light causing the surrounding gas to fluoresce, to glow with vibrant reds and blues and greens. Other nebulae are dark and quiet, cold clouds where the only light is the faint glow of distant stars shining through them, creating silhouettes, shadows cast against the background of the galaxy. These nebulae are where the cycle continues, where the matter that was once light becomes light again, where the elements forged in the hearts of dying stars are gathered together to form new stars, new planets, new worlds. It's a slow cycle, a patient transformation that takes millions of years, but it's always happening, always unfolding, the universe breathing in and out, matter and light changing places, energy flowing from one form to another. Nothing ever truly lost, nothing ever truly created, just an endless rearrangement of the same fundamental stuff. Consider the Orion Nebula, one of the most studied and photographed objects in the night sky. It's a stellar nursery, a region where new stars are being born right now, where gravity is pulling clouds of gas together, compressing them, heating them, igniting the fires of fusion. When you look at images of the Orion Nebula, you're seeing light that left those stars just a few thousand years ago. Light that has traveled across the gulf of space to reach your eyes. Light that carries information about what's happening there, about the temperature and composition and motion of the gas, about the age and mass and brightness of the stars. Every photon is a messenger, a tiny packet of information about the universe. And when we collect and analyze those photons, when we spread them out into spectra and study their wavelengths and intensities, we're reading the universe's story. We're learning its history. We're discovering its secrets. And the colors we see in nebulae, those brilliant reds and blues and greens, they're not arbitrary. Each color corresponds to a particular element, a particular type of atom, glowing at a particular wavelength as its electrons jump between energy levels. Hydrogen glows red, oxygen glows blue-green, nitrogen glows red-orange, and the combination of these colors creates the intricate patterns and structures we see in telescope images. It's atomic light, the light of individual atoms responding to the energy around them. And it tells us exactly what the nebula is made of, how hot it is, how dense it is, how fast it's moving. Light is not just illumination, it's information, it's communication, it's the universe speaking to us in a language we can decode. And when we think about matter as light slowed into a stable form, we're not just talking about a scientific theory, although there is real science behind it. Deep and beautiful science that connects relativity and quantum mechanics and thermodynamics. We're also talking about a way of seeing the world, a way of understanding our place in the universe. We are not separate from the cosmos. We are part of it, made of it, expressions of it. The atoms in your body were forged in the cores of ancient stars. The energy that powers your thoughts and your heartbeat and your breath came from the food you ate, which came from plants that captured sunlight, which came from the sun, which came from the gravitational collapse of a cloud of hydrogen billions of years ago, which came from the Big Bang, which came from, well, we don't know. We don't know what came before the beginning, or if there even was a before. We don't know why the universe exists, or why it's made of the things it's made of, or why it follows the laws it follows. But we do know that everything is connected, that matter and energy are two sides of the same coin, that light and time and space are all woven together into a single fabric, and that we, as conscious beings, as creatures made of stardust and sunlight, and the quiet hum of quantum fields, have the extraordinary privilege of being able to contemplate all of this, to ask questions, to wonder, to imagine, to dream. There's something almost magical about the idea that you and I, and everything around us, are made of light that has learned to hold still, energy that has decided to take on form, waves that have become particles, motion that has become structure. It suggests that the universe is not a cold mechanical thing, not a random accident, but something more like a work of art, a symphony, a story being told by reality to itself, with us as both the storytellers and the characters, both the observers and the observed. And perhaps that's the deepest meaning of the idea that matter is light slowed down. It reminds us that nothing is truly solid, nothing is truly permanent. Everything is in motion, everything is changing, everything is temporary and beautiful and fleeting. The mountains that seem so eternal will one day erode into dust. The stars that shine so brightly will one day burn out and fade. The galaxies that spin so majestically will one day drift apart, separated by the expansion of space, growing darker and colder and more isolated, until the universe itself becomes a vast, empty, silent place, where nothing moves, and nothing changes, and nothing happens anymore. But that's trillions of years from now, an almost unimaginable span of time, far longer than the universe has even existed so far. And until then, there is light, there is matter, there is life, there is consciousness. There is this moment right now where you are listening to these words, where your mind is wandering through the cosmos, where you are part of the great dance, part of the endless transformation, part of the light that has slowed down just long enough to become aware of itself, to look up at the stars, to wonder where it came from and where it's going. Some scientists have even explored ideas that sound very much like matter being frozen or condensed light. Recent research has suggested that in the very early universe, certain particles might have existed as massless, light-like entities, moving at incredible speeds, nearly indistinguishable from photons themselves. But then, as the universe cooled and conditions changed, these particles underwent a kind of phase transition, like water turning to ice. And suddenly they acquired mass. They slowed down, they became heavy and stable, and they formed the dark matter that now holds